Okay. Okay. So welcome back to CSCI 310 cybersecurity. Okay. For today's topic, so we'll be related to our new topic with cyber will be the cryptography and related to the network security. Okay. We'll start with the lecture. So we have pretty long lectures for coming like for this month. We have several chapters have to cover, and also I provide another one is related to the cryptography. So it have some introduction about some like what's the more details about like symmetric and asymmetric encryption, or also like hashing and some digital signature. So we can use in the code. So I'm not going to cover today for this part. Okay, if you're interested, then you can look at it and look at some example for some like let's say calculation. Okay, and also I provide some like source code. So those source code will in different language, like let's say in Python. So how can we use the cryptographic like cipher? So you can use the encryption key AES, or right now you maybe have no idea what they're doing. So like after the cipher and decipher, how can we encode the original plain text to the ciphertext like this? And of course, in the lecture, we will cover certain keywords. Okay. So right now, let's to move on it. So one thing, right here. So there are certain contents like the called the romance like PowerShell. Of course, later in the assignment, so kind of will be your the assignment related to the cyber graphics. So later you have some questions like we're going to do, including the how can we calculate the asymmetry, and also I will give you a question related to the like how can you change the Roman shift. Okay, so those will be related. Okay. In our network, so in the network, we have some security model we need to think about. So from the sender, sending the information, or sometimes we say the package to the receiver, okay? And sometimes we will include certain trusted third party, okay? So including maybe some distribute of secret information, or when we learn the TLS, SSL, some certificate, so we will like get it from the trust third party. And when we send it through, we have certain channel, okay, information channel. So we will try to encrypt it. So we try to secure the message, okay? So through the information channel and then to our receiver. Okay, so of course, like we have some like man in the middle, some certain attack to try to decrypt it. So there's like some opponents like included right here, information channel. So there's like whole network, okay, in this model. And for the opponents, including like maybe no matter the hackers or certain software try to access it, so they will like try to access it to the through the access channel, okay, and then go through the like the gatekeeper. So gatekeeper may be your including your firewall, or maybe use some like software application wherever, okay, and then they try to pass it to like access to your data software, or including some like in here we also try to add some internal security control. So those like gatekeeper as well as like the firewall, or anything like equivalent, or some like password based login, so it's possible. And then for the internal security control, will include like the access control. If you remember our we talk about IAM, so like permissions, access, and then of course we always talk about logs. Okay, so different logs and all these. Okay, we make sure the integrity and also our virus scans. So that's how we like look into it. And what's the issue? So we need to think about the in the our network security. So first, like how about the distribution of our secret information? How can like when we need to exchange the information, so how can we make it more secure? Okay, so because it's more important, how can make those information like being protected? Okay, and also how about our communication protocols? Okay, so what's the effect? So if we given a higher security, but with low latency. So all these like we need to be like considerate. And also, of course, the encryption. Okay, the encryption, what we say is the cryptography. So we're talking a different type like asymmetric, hashing, all these like if they're used like they should be like careful and correct. Okay, so some people say, okay, why don't we just like make it really high secure like multiple? So we do have a trade-off like when we have like make it more secure, that means it costs much more time, okay, to decrypt. So it will slow down the transmission, okay, for communication. That we need to think about that. So how can we provide several different security services, okay, and also the physically or logically placement of those like security mechanism, okay, and then the counter measurement. Also, we need to also consider if you use it. So maybe we have the failover and then maybe some error. Then how can we go do it? Okay. And when we talk about the cryptography logic, and then it's under it. Okay. And then we have the cryptography and also like cryptographic crypto crypto analysis. Okay, under the cryptography, we have two types. One is the related to the public key. Okay, so those like integer factorization, discrete logarithm. So those will be using the public key. And then also we have the private key. So if you remember we use the asymmetric. Okay, so we use the public key. Okay, encrypt and use the private key to decrypt like this standard. Okay, and also we have a block or cipher or stream cipher, two different. So when you see the term words like we talk about encipher, that means also is the meaning of encrypt and decipher. So we try to decrypt it. Okay, and the modules operation is we using a lot for our encryption for our cryptography. Okay, so that's why we need to learn what's mode. Okay, so when we asking what's the 27 mode 5, okay, or if you using a writing a program, you see the percentage sign. So it's we call it modulus. Okay, so it's the same. So if let's say we have a like let's say like ARM, okay, so they are all integers, and then M should be like that should be like greater than 0. Okay, so when we writing, okay, so if A, okay, so equivalent that equals to like R mod M. So we are representing if the M divides like R, okay, minus A or like A minus whatever. So we try to maintain is like R is greater than or equal to 0, but also less than M. So M we call it is the modulus, and then R is the remainder. Okay, and we need to like be sure like R is like positive or 0 like this. And when we try to add this, that means like A will be equals to M times Q. Okay, Q may be just like the quotient. Okay, any integer. Okay, other integer and then plus the remainder. So will be equals to A. Okay, so right here you see when we model M and then it will like getting the Q. Okay, so let's say if we have 42, okay, 6 mod 9. Okay, so we say this. So when 9 divides like 42 minus 6, it will be 36 like this. So the model is 9 and remainder is 6. And also 9 can like also let's say divide like 6 with like is 42 with the negative 36 like this. So it will be showing like if 42 demonstrate equals to 9 times 4 plus 6. So Q can be 6. So that's how we talking about. So here's the modules like that we return value that right here. So the modules will be the one affecting like we are using a lot, so like depends on the result, like controlling the how many numbers like what we're going to use. So this one is the modules. And sometimes we checking, okay, so after the modules, then what's the value of it? Okay, so we can determine. And something related to the math. Okay, so we have some like elementary numbers like theory. Okay, so we have some natural numbers. When we say natural number, so it would be like from 1, 2, 3 up to like 4, 5, like keep going. And when we say whole number represented by W, W will be including 0, and then when we say integer, Z, okay, so an integer we're including the negative numbers, okay. So if we say for divisor, let's say numbers b, so say divide a, so if like a goes to m times b, so for some like m where's like a, b, m, they are like under like belongs to the z. Okay, so that means they can be a negative, 0, or a positive number, so natural number. So will be like this. Okay, so we can like write in this one like b slash a like this, stroke a, and then we can like say okay, b divides a like this. Okay, and but this part is more like the about math, so we quickly for some definition, when we learn cryptography, we have to work on something related to the math. And for some common property, let's say a one like this, so maybe like positive one or negative one if we are divided by, and then or no matter like which order, so that means that we say AB or BA. So it will be like can be the positive B or negative B. Okay. So any of them, they the subset of Z. Okay. So when they divide, so divide 0, so that means that B cannot be equals to 0. Okay. Or BG or BH. Then we have one thing is like if they have a common let's say NG and H right here, so all of them will be a subset of Z. Okay, and so all the positive like divisor of 42 can be like 1, 2, 3, 5, 1, 2, 3, 6, 7, 14, 21, 42 they can be. Okay, so that's why we say and then we can choose like 21, 6, and then choose like NM will be a subset of Z. Okay. And also we will use a lot using the prime number. Okay, so in the later, so when we choosing the for asymmetric encryption, so we choose the prime number. So prime number is the integer p. So we say if a prime number, so it's the only positive divisor one at itself. Okay, so there's no others like divisors can be used. Okay, so on any integer can express as a unit product of the prime numbers, so they can like raise the positive integer power. So we can do it in this way. I see like this like 3 times 3 1 times 29 will be like 3 power 2 times like 29 power 2. Okay, or like 2 times 27 times 109. Also we can like change it. Okay, and all this like process we call the prime factorization. Okay, and next we have the greatest like common divisor. Okay, GCD. That's what we use later in the encryption tool. So this we need to know. And we have the greatest common divisor. So we will try to looking for the largest divisor both for A and B. So these two integers. Okay, this. So if I give you two integers A and B, so those like positive integer, maybe C, if there is there GCD. Okay, so if and only if. So if no in math we always use this terms like if and only if. That means you're going back. So no matter like A CA or CB, so we're talking about, so any divisor B, both A and B also divide C. Okay, and then for the notation we're using the GCD AB will be equals to C. So if we need to find like what's the GCD of like 4963, so 49 will be like 7 times 7, and then 63 times like 9 times 7. So what's the common GCD will be 7 like this. And relatively prime number, so we will choose the one. So we will try to pick the number. We say there to be like relative prime if their GCD is 1. Okay, so we have like two numbers, 63 and 22. So we can say it's a relative prime. So for their GCD, because they only have like 1, that is common. Okay. And how can we determine two numbers, their relative prime? So we just need to find all their GCD, and those their like try to find their prime factors. Okay, so if they don't have any common prime factors other than 1, so they would call the relative prime. Okay, so if 63, we can use that 9 times 7, or 3 power by 2 if we remember right here, and 22 will be 11 times 2, like this. So they don't have any other common prime factor. Okay, so they only have 1, so they can call it relative prime. Okay, and when we come back to our modular arithmetic again, okay, when we come back to here, so if like A equals equivalent to what's like B mod M, so only one thing, like it's like M is where A a bit divided of like A minus B. Okay, so when we look at, so A is congruent to the B and modulo M. Okay, so M requires the modulus, as we say. So right here 27A and then 2 mod 5. Okay, so right here B will be the remainder. Okay, so after dividing A and by the M, but one thing, okay, right here, let's say 27, 7 mod 5, or like 7 right here, like 2 mod 5. And when we move forward right here, so B mod M, so when we like putting it like to inside B equal like A mod M 2, so will be 27 mod 5 2. Here's the B right here, right, the remainder. So we can consider always try to get the smallest like positive remainder. So we sometimes got the residual, okay, right here. And for our module operation, so this like operation, we try to reduce some infinite set of integer, so to a finite set. Okay, so we have like modulo 5 operation, then we have a 5 set. So you will see right here, so -10, 5, 0, 5, 10, like this. So it's all the remainders, so mod 5, okay, like this. And something like 1, so what's the when they 1 mod 5, okay, so that means the remainder will be 1, and then 2, so will be mod 5, so the remainder. So you see a pattern right here, and those of these like set, so we will like modulo 5, they have 5 elements, so it will be 0 to 4, 0, 1, 2, 3, 4. So it will donate like Z5 like this. Okay, and so very quickly we talk about some math, then we will move on to about the some history, like some brief history. All these like encryption algorithm. So we did from the BC to like 1976. So we call it like secret key algorithm, and we can call the private key algorithms, or like symmetric key algorithm. So you see it. Okay, Julius Caesar. So we use a substitution cipher. So this one will be the first one we introduce. It's called the Caesar cipher. Okay, and then it will kind of widespread used in the World War II. Okay, and we have the called public key algorithm later introduced. Okay, the Wakefield Diffie and the Martin Hellman. So they will introduce. And for the crypto system, so far we have like talked about the E. E will be the set of encryption function. Okay, and that maybe we denote by the M times K will be like given the C cipher, or the decryption D. So that means the C the cipher like times K and then go back to M. Okay, so M will be the plaintext. So this one will be, that means the original message, and K will be the key. Okay, so right here we always talk about it. And then C will be the set of like ciphertext. That means the encrypted message. That means we have an original plaintext, the original message, meaningful, meaning those like context meaningful message. Okay, so after we encrypt it with certain key, okay, and then change to ciphertext. And those ciphertext, when we use the key again, so we can change decrypt it, okay, decipher it back to the original message. That's like how it works. Start with the most common popular symbol like we know, and we can able to find the patterns. Is called the Caesar cipher. Let's say, so we have an original like M, will be the sequence of the letters. Okay, and we have a key. So this key will be using I. So I will be the integer from between 0 to 25. Okay, so actually this one is the numbers of the how many English letter. Okay, and E under with the encipher, so will be like the E K will be the subset, the K will be key, so we are going to use for all the letters. And when we for the M, that means the sequence of the letter, we will pass the K and mode 26. Okay, so there's a key. So after we mode K, so we're getting value, and D will be the cipher too. So we will add the 26 at the C and minus K and mode 26. So this one we can decipher it. So it changes, like it will become the same. So whole action right here, they will try to replace like each of the letter in the plain text. So with different one, they fix on the number based on the alphabet. Okay. So this like cipher just like really illustrate here. So they will use the left shift of 3. Okay. So if I have an original one, so let's say for the key is 3. So I'll do the left shift. Okay. So E right here, 1, 2, 3. So we go to B. So pretty straightforward. So it's the C cipher. Okay. And if we look at the example right here, so start with the beginning. You don't have worry if in case I have like some question asking you how can we do that? Maybe we start with like maybe just follow this table. Okay, A everything 0 and then Z will be 25. Okay, 0 to 25. We convert, okay, let's say start with like 30, and then we will like add it and mode 26, like we need to convert. And then after mode 26 will be a model like will be 4, the remainder right here 4, and then 13, 20. So if any number greater than 24, it like go back to the beginning like this. And that's how we're going to encrypt it. So it will become like 4. So where we representing 4. So if you know like V right here with 21, okay. And you say, what's the key? So right here, you see we are trying to adding the 9. Okay, so right here, the K is 9. So every time 21 plus 9 will be 30. 30 mode 26 will be 4. Okay, and 13, what's the value? How can we get with 4 plus 9? Okay, will be 13. Okay, 13, and we just like look up on the table, 13 will be N. Okay, so pretty straightforward. So it's a simple math. Okay, so once you know how it works, so if you see a question like this, it's a pretty straightforward. So most of the question maybe you need to find what's the K. Okay, what's the key? So what's the number? Then once you figure it, then you know. And if for the decipher, so if we have the value E, right? So we will based on the value. So let's say we have 21, and well minus like the K would be 9. Okay, so and also we add back the 26. Okay, and we mode 26 again, so we will convert back will be 21. Okay, so pretty straightforward, and then we will get all the value back. So this how can we decipher it? Okay, everything just like follow this the tables, then we can able to do that. And how about the attacks are going to happen? Because at first we only have like Y, okay, for the cyber attacks, right? So only our target, our goal is try to find the plain text. So what's the key? So if we're using the cyber attacks, like for this one, the CSCI cipher. So once we're able to get the K, the value, the key, okay, we know the number, then we know how can we are able to know the original plain text. So let's say if we did not have a XY, then we still left finding the K. And maybe for some like chosen plain text, we can do it, get some specific plain text to encipher and then to get it. So most of the time, if you look at the decipher text, like if you couldn't read it, that means the key is incorrect. But you know, because like for the key, because it's a shift, right? Okay, so you can start from shifting 1, 2, 3, 4 until like maybe 25. Okay, so no, within a short period of time, you are able to figure out what's the key. Okay, and for the crypto analysis, so actually we put it call it like it's an art or science. So it try to like breaking an encryption scheme. Okay, so we try to looking for those like characteristics of those algorithm, or like we using math. Actually, most of the encryption or decryption we are just like using the math. Okay, and then we try to recover a key so we can use it to break manage our cyber attacks. Those things. And for the burst and force, so we will trace all those like possible key on a piece of the cyber text. So if the keys they're small, so we kind of like able to break it easily, but it's long, it takes sometimes. And if you remember, we talked about the password, right? Nowadays, the password, it requires you to have uppercase, lowercase, and then special character. Okay, and then the one who introduced this one, and actually it was it should be last year's. Okay, we remember in last year. So he came and say, okay, so he came and apologized. So actually, he approached to make the password like recommended so complicated. We are not saying because like what he says like the length of the password is more important to the combination of the password. Okay, that means like if you have a longer password, okay, it's better than you have a combination of all this, but it's short. Okay. For the attacker programmer, because like for the combination, but short, it still like have a shorter time to break it. Okay. So that's why like if you're using more complicated mix of it because you have more letters, but with really long. Okay, compared to like maybe 10 digits of password to 100 digits of password. Of course, 100 digit numbers it takes longer than 10 digits like max. Because like for mix of the character maybe like from A to Z, okay, A to C, 26 uppercase, lowercase, and then we have the numbers, special characters, all this like, and also the use of the special character, actually they're kind of limited. Okay, so compare of this, longer password would be better. Okay. And the classical cryptography is the idea. So start by at least sending content to Bob. Okay, so we have a plain text and then we try to encrypt it. Okay, so we're using the algorithm. Okay, and after we encrypt, we will send it through the some secure channel. So we have the cipher text Y. Okay, the crypto analysis we try to check it. So what's the original text base X, or like the what's the plain text what they receive, like what's the key of using it. Okay, so we using the key source, okay, to like encrypt it. So cipher and send it, okay, through the some secure channel, and then once about it knows like what's the key source, then we use the algorithm to describe it, so we can obtain the original plain text. So here's the whole the flow of like sending the message with the key. Okay, and in this that we introduce, like actually if you know more than that, then but just like back to our first step, we basically when we know that we share the common key, so we know, so this key is a common. Okay, just like the CSCI cipher. So that what's the key? Let's say I tell you the K is 9. So I use it using the left shift to 9, and then this time that you move back like 9 like to the shift right, okay, by K, then you know already know. So we have a call as a name is called symmetric. Okay, so that means like what's the symmetric? So it's paired okay, left and right. So they were saying, so it's a symmetric cryptography. Okay, so for the key using for the encryption and decryption, they are same. So we call it a symmetric cryptography. And we have two basic type of like cipher. One is called the transposition, okay, and then one is the substitution cipher. And or we can have the porter cipher, so we can just like combination of these two basic types. of them. Okay. And when we look into like more classical cryptography right here, let's say we have the Y, that means that we're using the encryption using K and pass the plaintext, and we will receive the ciphertext. So this one is a process of encryption. And for the plaintext, so we will pass it like we need to like decrypt it by passing it, and then we receive it X, so original message, and then we have encryption and then the decryption key. So because it's symmetric, that means the key is always the same. So they must like you see the function, okay, encryption or decryption function. So they must be the inverses of one another. Okay, so that means if you try to encrypt a decryption key, so you will still getting the same Y. So if there's if I give you the question asking you, well, okay, so if I have a original plaintext original message, so after encryption, what's the result? And also remember, this is a part you have to validate. How can you validate? So try to like trace back. Okay, so you should get the same result. So we like we inverse like one another. So you need to like check. Okay, that means like after you maybe I give you the encryption text, okay, the ciphertext. So after you decrypt it, and then if you can use the, if it's a symmetric encryption, can you like decipher it and then cipher back? So it's the same, and it's a ciphertext or deciphertext. So it match, that means your key is correct. Okay, so it's the logic. For the transposition, we will introduce like example is called the we arrange the letter in the plaintext to produce the ciphertext. So one of the examples is reference cipher. Okay, so right here we say the plaintext, let's say hello world, we always change it, and then we will arrange it. Let's say we change it to HLOOL. So you will see E change to L, and then L change to O, and then O will be L, like right here. So they will change like they will just like move around. Okay, right here. So this one is called a transposition, the ciphertext, and then row right here E L W D R. So they'll move right here W E R and then E L right here. So they'll just like move. Okay, so you see the red in color, transpose right here, L, red. Okay, so you see a pattern, right? So H L O O L right here. So here's called a transposition. And for the attacking the cipher, so how can we? So maybe we have the called the anagramming. So we're giving the frequency. So it's a 1 gram. So for the frequency, so they will match the English like frequency. So for other n-gram frequency, they do not. So they probably will be the transposition. So what's this mean? So we maybe when we try to rearrange the letter to form the n-gram with the highest frequency. Let's say for the ciphertext right here, so you'll see maybe meaningless, right? When we try to looking for the frequency of the 2 grams at between beginning with H, we given a number beginning with HE will be 0.0305, HO will be 0.0043. Okay, if something like starting begin with HL, HW, HR, HD, they will less than like 0.601. Okay, so that means the frequency. What's the frequency is telling? So okay, if we're starting with HL is pretty low, then maybe I don't think this is the original plaintext. Okay, it'll be cipher. Okay, or like the frequency of 2 gram ending in H. Okay, let's say what's the something ending with H, with WH will be 0.0026. Okay, or like EHLH or something will be less than 0.0002. Okay, so we kind of like implement. One thing is like E is like follows the H. So we just like picking the numbers and with the n-gram frequency. So we say, okay, so that means probably when we change it, so HE with high, so we will arrange like with adjacent, so we are right next to each other, and then with the course of this So we try to like read off a course and then go start. So we will able to get the original plain text. So we may, okay, maybe for the gram HG it's better LL, will be more like OW, okay, row OR LD. So like keep going down. And for the substitution cipher, so substitution cipher will be change the characters in the plain text to produce the ciphertext. So the one we use is called the CSCI cipher, right? So remember the original will be hello world, and then we're using key 3. So we will get the letter like D like this. So we will the ciphertext will be KHOR and then ZRUOG like this because the key. So we do the left shift by 3, okay. And then when we're attacking the cipher, okay, we have burst force, so it's kind of like exhaustive search. So if the key space is small enough, we can just like try all the possible key, okay, until you find the right one. For the CSCI cipher, we know it only have 26 possible key. Like everyone knows it when I tell you, okay. So try 26 times if you are writing a script, okay, using your familiar language. Let's say you know C++, Python, Node.js, whatever. You can just test of them, then you're able to get it. So you can print out of them and then to see which one have a meaningful message, okay. And also we can do the statistical analysis. So we just like compare to the 1 grams mode of the English, just like what we see. Let's say for the ciphertext, we will check like with the K, and then we're looking for all those values. What's the each letters in ciphertext frequency? So if we look at all these, maybe like G 0.1, H 0.1, K, and then O with like 0.3 is highest. Okay. So if you remember always the hello world like this, and then we can matching okay K 0.1 and then come from ours 0.2. So we just like checking. So you'll see right here, so more all those like frequency like A, B, C, D, I keep going to Z. Z. Okay, so you tell commonly the word comes out with Z will be like really low 0.002. Okay, A 0.08. Okay, so will be like this. So we can check the frequency. And what's the equation? So when we need to check the frequency of the character, so the C in ciphertext. So we need to show the correlation of the frequency of the letter in the ciphertext, so corresponding the letter in English. So if we are assuming the key is I, so because we know that ciphertext should be where there's some between 0 and 25, right? So right here, so we can just put, okay, let's say if I need to find first like letter, so let's 0.1, 0.1, okay, and then with the surface state and then minus by I, okay. And just assuming because we have the original text, so just like we put like the letters like 1 by 1, then you can get it. And what's the px will be the frequency. So right here will be a characters in the English. So we can try to like look for the maximum correlation. Okay. So once we get all these like correlation, getting the I. Okay. So possibly, so maybe like let's say maybe I equal to 3 will be 0.05, 6, 10 like this. Okay. So we maybe like choose from like 3, 6, 10. Okay. And when we like when I equal to 6 and then we shift it by it, so it will like try it. So let's say if you remember the equation, our ciphertext equation, okay, CSCI cipher, so we just like shifting it, right? So we can pick those like high possible like probable keys, okay. And finally we turns out like we can find from 6, 10, 3, 14. And we'll say, okay, I can read something when I equals to 3. So the plain text is hello world. Okay. So we'll know, okay, only one English phrase we can read it. We have some meanings. So it will be 3. So we can say the key 3. Okay. So here's the way we can use like for the frequency engram. And so what as far as say when we look at the CSCI cipher, this problem is like too short. Okay, the key is too short. It's so easy. We can use the enhanced exhaustive like search like to figure it out, and also for statistical frequencies, like they're not considered relative, so it may be like too much like the regular English letter. So maybe is there any solution other way? So we say like always make longer, right? So we have like multiple letters in the key, okay, or like maybe make it like smooth the statistical frequency. Okay, so make the cipher analysis like harder. So make it more like challenge. Okay, so instead just like the Caesar cipher, so we will change it. Okay, so we will change it as a phrase. Okay, so let's say we have an original like message. The boy has the ball. Okay, and if we're using the key, so the key we're using the VIG like this, like the key. So we can also still using kind of like Caesar cipher. So using it, so we will like change it the. So we will change it to the OPK. Okay. So instead of like changing together, so we will change the key. Okay. So we will like 3 3 3 like this, and then to change it. So that's how it looks like. So for the I will give you the like this. We have the triplet. Okay, so the truth will be showing the relevance like pass. Okay, so if you remember right here with the key VIG right here, and then we have some numbers. So this one will be the reference row again, also the columns only. So we're showing. So all this will be the example. Like if we have the key, and then let's say we have key V, okay, and then we try to match with the T, and we will follow the column goes down. So we'll see. So this one will be the letter to O, giving is O. So start from right here. So V and checking to T will be O. And also we have I. So if for I and looking for H, H will be right here P, okay. And then G, so we're looking G and E, so it matches with the K. So that's how we locate the so it will how can we like encipher it? Okay, instead just like showing one number, so we'll try to matching it with the tuples. Okay, so this one we will matching like from we will look at the which column. Okay, so keyword and then go down to the row, and then we can match it. We have some like useful terms like we need to know. So with the previous, so we talk about the length of the key. So we will say, okay, so when we say the previous 3, that means that we have 3 of them, like this is the length of the key, how many letters encoded, and then the triple. So we will, this is a table, so we are using to encipher or decipher. Okay, so this one, so we have the key letter on the top, and then we have the plain text letter on the left. So right now this one is pretty short. So right here, A, B, E, H, like right here. So we'll match. Okay. And once we have the even though you see, so that's why when you see okay, maybe I have 2L right here, but why we have different output? Okay, after the ciphertext. So okay, because for the previous, let's say our Caesar cipher, we will shift by the numbers, right? The K is the number. So if I know L will be let's say we shift by 1, 2, 3, so they should be same. But why not? Because they're not the same. So you're thinking, okay, it's hard to guess because they are you think key will be G and V. So if you look at the G and V, for L, they will be R and G. So they will be different. Okay. So they are not the same. So it will increase the difficulty to guess. Okay, and also we have like called the polyalphabetics. So these were different letters we can use. And for the Caesar cipher, so we say it's monoalphabetic because we just only one. And so far we go through all this. Because when we learning cybersecurity, we learn encryption, decryption, or like when we say and cipher tag, like and cipher, decipher, all this. Then we another way is that we know how to attack it, right? So when we need to attack this one, how can we need to maybe determine, okay, what's the key length? Okay, so if we know the keywords n, then the cipher consists some like the end of the Monte alphabet, like substitution in the cipher. Okay, so right here we are trying to looking for, okay, if the key will be like this, like E C E P T, and then like this, and then we try to match it. Okay, EPT right here. So and then for the plaintext, like we have something like red right here, and we try to match. And after we cipher, okay, the cipher text will look like something like this. Because we read it, it's like converted, and then like save yourself, it's like this, the meaning. So we do have some meaning, and then with the keyword, so right here, the key. And for the ciphertext, we have no meaning, but we try to looking for some patterns or some keywords that we repeated. So it's one of the method we can use. And because this time we know for the cipher like and hash we have maybe we can get a like random key, so at least like they are long as the message. Okay, so how about this? So they are probably like unbreakable. Why? Because like we think about it, if we have the ciphertext the XQR, okay, so they are equally corresponding. Like for the plaintext like this, we have a key AJIY, and then do it like this, and then plaintext don't. So they will convert another letter, another one. So for everything right here, for the key, we can tell like they must be random. So, or like when you try to attack the cipher, so when we maybe try to like we generate the key, so kind of approximation. So when we're using a pseudo random numbers to generate key, so you know they are not random, right? So in programming, because we try to generate random number, actually they have some like called a random numbers table. Okay, that's why sometimes in some computer, or like when you start to learn programming, they say when you're using ran, okay, to generate, they're not always random, they're always coming the same. And the reason behind, because they have a random tables, and they will be repeating. So unless you're passing a parameter to get a new another tables, okay, or sometimes you see we random passing with the every second, so we try to get the different tables for random generalization. So what is a question, but I just like quickly skip it, and there's some question, and here would be the more like it's a more complete table if you want to see. Okay, so leave your question, you can find, okay, if I want to find the ciphertext for the like mid release, okay, so if I use the key 4, then how can you get this question? And also, can you like try to decrypt it, the finding this one? So maybe let's say if I know the 4, so it's like how can we decrypt? So it's a kind of exercise, but just quickly um finish this part, and then just like kind of overview like right here. So later we will move in, so you see the data encryption standard. But so far I will stop and pause right here, and I would like to switch back to our, okay, I already closed it. For the lab exercise, I already give you the some code, and we can use for our cryptos. And I would like to let you to try and execute it and see the differences, because for maybe nowadays, like for different encryption method, we have already launched so many, unless you maybe like doing some certain research and try to invent or develop a new way to encrypt it or decrypt it. Okay. If no, maybe we are just like mix of different type. Okay. Of course, nowadays we talk about symmetric, but of course we do have asymmetric. Okay. And let me change the directory. So I would like to show you one thing right here. Okay. So first I would like to execute one is the cryptos JS. Okay, it's a JS file. So I'd like to run it. No, and then the crypto.js files. Okay, so if I have the original text, and I can tell like in the different type of encryption. So right here I'm using the algorithm is called the SHA-256. So for this one you maybe still not yet see what is this different type of encryption method. Okay, but of course later I'm going we do cover this part, but for right here, the exercise, okay, you can try to execute, and I want to give you some example. So you can like try to use different importing those like crypto library, which can help you, and then you can define the algorithm. And so far, if you want to use it, you can just use that cryptos and then create a hash and passing, okay, which algorithm you're going to use, and you can pass a function, update the key, and then digest it with like different type of output. So this one may be the hash encoding or base 64 encoding. So either way, so you can save the your ciphertext. Okay. If you want to encrypt your password, let's say like this, then you can use the SHA-256. Okay, so maybe I want to save it as a hex. So for most of people, when they look at it, they have no idea what's the meaning of it. So that's a pretty good idea. Or if you want to like more meaningful, maybe you can use the base 64. Okay, but right now you have no idea what's doing, but just need to execute and see how it works. Okay. And also I give you another Python script, okay, and it's a AES encryption. So pretty similar. So we also like import it. So the structure they're all the same. So we try to import it, and then maybe we will get some like random bytes for the key. Okay, 16, and then we have the data. So we have a message. So you see we were using the encryption. So keep passing the key, and then maybe like which type of the using the AES model. Okay, and then we will using the cipher and encrypt it. Okay, pair it with certain block size. Okay, we define from them their own default block size. Okay, and you will get it. Okay, and we can also have a result. So we execute Python AES encryption. Okay, so I forgot to install it. If you want to see, you can install it later. Okay, so right now I don't have modules installed. Okay, and let's go back to our the example I give you. So basically we talk about the symmetric, or later we talk about asymmetric. So I will start part of it just like recap of it. So we talk about the cryptography. So we talk about so it's the practice to secure our communication, like we know. So try to maintain our confidentiality, integrity, authentication, so CIA and non-reputation. Okay. So far for encryption or all the keywords we're talking about, like we're converting the plain text to ciphertext, and then we doing the decryption, converting the ciphertext back into plain text, and then we use the key for encryption and decryption. So for those key, sometimes we hear the term symmetric and asymmetric. So in our lecture part, so we do cover, so some of them, they will be the symmetric. And for the symmetric encryption, that means the key, they are same, okay, for the encryption and decryption. So one of the example is called the AES, Advanced Encryption Standard. If I go back to our lecture right here, so later we have the DS, Data Encryption Standard, and actually we already knew it. We have different round, and then later we have the AES too. But this part I will just keep it for later. So we will continue. I will record the videos and post it about the Thursday course. So we will talk about what's the AES, because we are still using, even though we say symmetric is using share same key, it's not that good, but why we still exist, or like you see still a lot. We have a AES. Okay. For actually, later we'll tell, even though we will use a asymmetric sharing the using our public key and private key, okay, to encrypt and decrypt it. But when we need to sending our key to others, like to encrypt it, or we need to decrypt it, okay, then we will use some method. Okay, because for the key itself, it doesn't matter. So we may be using the symmetric, maybe using the AES to send the key to the sender. Okay, because I'm the receiver, I need to send the key to the sender, so they can use my key to encrypt it. So when I receive it, I can decrypt it. Okay, so here's the logic in behind. Of course, we can, there's the steps start from the key generation. So we need to pick the key, different key, and then we can encrypt the inputs, just like in the programs that I show you. Okay, so we can choose like different key we are going to use, and then we can encrypt the data. And then for the process, we can choose the algorithm we are going to use, AES. Okay, maybe for CSCI, like for study, of course, we can use it. And actually, there's a website, online website. They are pretty several. Actually, there are several websites. So for testing, I would like to let you to try it later. So for exercise to find, also maybe in the assignment coming assignment I'm going to post. So you need to work on it. It's about like, okay, if I give you the maybe encrypted, then you need to find out what's the key. Okay. And then for the ciphertext output, so we get the encrypted data. And for the reverse process, so those like input the encrypted data to be decrypted, and then we using the same algorithm because we are doing the symmetric way. So using the secret key, so we'll get the original data. Okay, so if we have the, let's say for the AES encryption, and then I giving the key, so we'll cipher and change it ciphertext. So I'm just telling you like how it looks like. Because like we have the for the AES, so we will convert it into the primary format, and then we will go to several runs like the keys, okay, based on the original one we giving using the key schedule. So we will add the like the run key XOR and the first one, and then we will later we will doing the shift. Okay, so we will inverse the shift row, we'll shift it, and then they will inverse the sub the bytes and then add the run key. So they will doing the inverse the mixed columns like this. They will go through. So for the AES, 128 will be 10 rounds. Okay. So if you see some encryption, so we say that AES 128, that means the main round will be like 10 rounds for it. So we can do it. Of course, we can do it by ourselves. It's still possible, but of course, like it will be better using a computer like help us to like simulate it. Okay, so all these the steps is showing the final one. So we're doing the inverse shift one, and then inverse like sub byte, and then add the run key, so it comes out for the decryption. So it kind of like just like reverse the process. So after this, we will get the final output hello, because as you remember, if we try to no matter using, we try to test like decrypt the encrypt the files, or like encrypt the decrypt text, then we should get the same result. So here's what's the expectation. And for the later when we cover will be the asymmetric, then I will like move on to talk about, give some example with the asymmetric encryption. And pretty so if you use the download, if you have tried using the AWS tool, I ask you to download the key, the certificate, so that will be that one, that's our essay. So but this one we're going to cover, and quickly our lecture will be finished right here, and I will record the next part will be next one will be the encryption. We'll come back with the DES. Okay, So will be a data encryption standard. Okay, and thank you so much. Bye.